Hello, let us start our review with logic. We construct a truth table for the following statement: P and not Q, and P or Q. So the first two columns must be for P and Q. We have only two variables. It means that we must have 4 lines. So we always list the variables in the same order: T, T, F, F for P, and T, F, T, F for Q. So we can, for the first, the short part of the statement, P and not Q, we will also need a column for not Q. Not Q is the opposite for Q. If Q is T, then not Q is F. Q is F, then not Q is T, T, F, F, T. Now we can find all parts of the statement and the end of them. So first let us find P and not Q. Be careful to consider the correct columns. So this is P and this is not Q. We want to find end of the first and of the third column. And end is only true when both parts are true. So only in the second line both are true. In all the other lines, one of them is false, so end is false. Then we also need P or Q. P or Q. So we consider the first two columns. Or is only false when both are false. If one of them is true, then or is true. So first, second, third line, all are true. In the last line, F or F is false. And now the last column, the resultant column, is the first statement and the second statement. So first, second, so this is first, second. We compare these two columns and we want end of them. End is only true when both parts are true. So in the second line we have T. In all other lines we have F. And this is our last column, the result column. So if your last column is somewhere in the middle, please show that it is your last column. It will be easy for me to grade. Let us make another truth table for another statement with conditional. So it is also the statement containing only two variables, P and Q. We start with the same two columns in the same standard order: true, true, false, false for P, true, false, true, false for Q. So, oh, here's R. No, I don't want to have R here. Let us change it to P. Q or P. If Q or P, then Q and not P. So we need also the column for not P. So you will have only two variables on the exam. That's why I'm making example with two variables, P and Q. In the homework I couldn't find there's similar problems, so in this assignment, review assignment, there's a problem with three variables. That's why the table in the review assignment in MATH1300 must have 8 lines. So if you have only P and Q, so only two variables, then you have only 4 lines. Okay, so we have the column for not P. It's the opposite of P. T, F, T, F, F, T, F, T. Now let us determine the values of each of the small part of the statement. Q or P. We compare the first two columns. Or is true if one of them is true. So only in the last line we have false. T, 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 F. Then we have Q and not P. Q and not P. So second and third column, and is true when both values are true. So in the third column we have T, in all other one of the values is F, so the and is false. F, F, true, F. And the last column is for Q or P, then Q and not P. So first, second, if this, then this. So order for conditional, order is very important. For and or, order is not important. So Q and not P, or not P and Q, it doesn't matter. For conditional, it's very important. So, and this part is the hypothesis. This part is the conclusion, and the conditional is only false if hypothesis is true and the conclusion is false. So when hypothesis is false, conditional is true. Doesn't matter what is here. If the hypothesis is true and conclusion is also true, then conditional is true. But in the first two lines, hypothesis is true, conclusion is false, then conditional is false. This is our final column, FFTT. Decide whether the argument is valid or invalid. We won the game or they won the game. They did not win the game. We won the game. So such an argument must be solved by truth table. Maybe you can find there sometimes especially in my MATLAB homework, they suggest to remembering the names of special syllogism, but it doesn't work always. Sometimes the best way is to construct the truth table. So first we write the syllogism in symbolic form. Let us call V won the game P, they won the game Q. So the first statement is P or Q. They did not win the game, so they is Q, so the second statement is not Q. Therefore, we won the game. Therefore, P. If you know the name of this special form of syllogism, you can say if it is true or false directly, and if it is not one of the special syllogism, or you don't know the name, you can always make a truth table. So in the truth table, both premises and conclusion must be represented by a column. So we have two variables, so we'll start with the same four lines, P and Q, and we list variables in the standard order T, F, F, T, F, T, F. Then we also need a column for not Q, the opposite of Q, F, T, F, T, and this is one of the premises. The second premise, P or Q, P or Q. So or is true if one of the truth variables is true. So in the first three lines, or is true. In the last line, when both are false, or is false. This is the second premise. And then the line for conclusion, I will write P again because it is we want to consider it separately. So the rule for proving a syllogism is in the lines when both premises are true, we have one such a line here, we look for the truth value of P. Truth value of P is also T. So in this line, conclusion is true, it means the syllogism must be valid. Let us do it for the next one. We have it already in symbolic form. Let us start with the same first two columns for P and Q. T, T, F, F, T, F, T, F. Then we need columns for premises. The first one is here. The first premise is P. Then not Q, if not Q, then not P. So let us make column for not P and for not Q. Not P is the opposite of the first column, F, F, T, T. Not Q is the opposite of the second column, F, T, F, T. And the premise itself will be not Q, if not Q, then not P. If this, then this. This is the hypothesis. If hypothesis is false, then conditional is true. If hypothesis is true and conclusion is false, then conditional is false. And here T, T, T. So this is the second premise. Now we look into the lines where both premises are true. Here and here, here and here. In the rest, at least one of them is false. For this line, we look at the truth value of the conclusion, not Q. Not Q, false, true. So there is a line where premises are true but conclusion is false. It means that syllogism is invalid. Chapter 4, graphs. So we have two different graphs here. Let us decide whether they are connected, which vertices are odd and even. Let us start with this small graph. Of course, it is connected, since we can come from one vertex to another without any problem. This connected graph consists of two different parts, not connected to each other. Both graphs are connected. Now, odd and even vertices. Odd, even. So we count the number of lines coming to this vertex. So the vertex A has 3 lines. 3 is an odd number, so A is an odd vertex. B, the same, 3 lines ending up at B, so B is also an odd vertex. C, 1, 2, 3 edges and at the point C, so 2 edges end at the point C. 2 is an even number, so C is an even vertex. D, 2 lines, 2 edges, 2 is an even number, so D is an even vertex. So here, odd vertices, even vertices. A, 1, 2, two lines. So they are not straight line, but still two lines. So A is an even vertex. B, 1, 2, 3, three lines, odd vertex. C, 1, 2, 3. Three lines end up at C, so C, 3 is an odd number, C is an odd vertex. D, 1, 2. Two edges or two lines end up at D, so D is even. A, B, C, D, E. E, 1, 2. Two lines, E is even. F, 1, 2. Two lines, F is even. G, be careful, so many lines, let us count them carefully. 1, 2, 3, 4, 5. 5 lines, an odd vertex, G. Oops, it's not G. G. And the last one, H. 1, 2, 3, 3 lines, an odd number, so H is also an odd vertex. On the edges, so in the graph, edges are the lines connecting vertices. 1, 2, 3, 4, 5. 5 edges. In this graph, it's not so easy for this graph because not all intersections are vertices. Here, for example, it's not a vertex. So be careful. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 edges. So are there any bridges? Also, the question that can be, so the bridges are the lines that if you remove this line, the graph will be disconnected. So if you remove any of this line, the graph will still be connected. I will show you the example of a bridge. So in this graph, this is the bridge. If you remove this line, this edge, then the graph will consist of two separate parts, not connected parts, and will be disconnected. So in these two examples, we don't have any bridges. Now the next part, we have here a weighted graph, and we will use nearest neighbor algorithm to find a Hamilton circuit that begins at the vertex B. So nearest neighbor means that we start from B and find the edge with the lowest weight. So we have here 1, 4, 8, and 5. Of course, 1 is the best one, the lowest weight, so the cheapest weight. So from B, we go to C. Now we look from C, we have 7, 5, 6, 5 looks to be the best one. So from C, we go to E. From E, so I will sketch how I move. I don't want to draw on the graph, so we move this way. So from E, we do not consider this H, because it will return us to B. We consider only these two, 2 and 1. course 1 is better, we go to A. So go to A. And from A, we have only one way to finish our graph. Hamilton circuit. In Hamilton circuit, we visit all vertices. We don't want to visit every line, every edge. We want to visit every vertex or city, as it was in the examples. So the last is D, and then we return to B. This is the nearest neighbor algorithm for this graph. So let's consider the second graph. So we start also, let us start from vertex B. The lines have weight 10, 10, 7, and 4. 4 is the best, and we go to E. From E, we have 14, 17, and also 14. So not a very good example. Let us change this one to 13. So 13, maybe it was example for best stage algorithm. Okay, so 13, 17, 13, we go to D. And then from D, we have to choose between 6 and 14. Of course, we choose 6 to C. And then, so we move this way. So, and now the last vertex to visit is A and return to B. Let us use best stage algorithm. To find the Hamilton circuit for this graph. This is a little bit more tricky. We first find the very best edge in the entire graph. So, and it looks to be this edge BE, with the weight 4. So we do not list the vertices in this method. We choose the edges one after another. So let us make a sketch. So here all our vertices C, D, B, E, A. We choose this edge and connect B and E. Then we choose the second best edge, and this is CD with the weight 6. Our second edge shouldn't be connected with the first one. We just choose the edges and then we connect them. So the third edge will be with 7. Yes, with 7, BA. It works. So sometimes we cannot choose the third edge when it comes from the same vertex. So for example, if we have situation like this, 1, 2, and the third best edge goes like this, we cannot choose this. If the third edge connect these vertices, we cannot choose this. In this example, we can choose the third edge, AB. And then on the next step, actually we have only one way how to finish this circuit, because we cannot connect like this. We can only connect, oh no, wait a minute, we have 2 ways to finish it. That's why we look for the next best edge. 7, the next is 9. So C and CA is 1. And now the last edge will be DE. Then we look in the body of the problem. There is written list starting from the vertex B. So let us also list the vertices from B, starting from B, B, E, D, C, A, B. So there is another way to list them in the opposite direction. B, A, C, D, E, B. It's actually the same circuit. If the question asks you to find the weight of a circuit, you add all these weights together, or in this B, C, E, A, D, B, let us find the weight of this circuit. BC is 1 plus CE plus 5 plus EA plus 1 plus AD plus 8 plus DB plus 4, so 10, 19, the weight of the circuit.